Log on, tune in, find out. Another good idea from Cambridge.
Sparse, which is good. Okay, so today we're going to talk, well, this afternoon we're going to talk about noise, and it's been delayed. And so it's very important to understand whether everything we discuss is robust to noise. Because if it were not, then we could just take the theory and trash it. And I think in real life, the reason it's important in real life, every time I'm going to make measurements, I'm going to build sensors, and we had two lectures on this already. In real life, each time I'm going to measure things, I cannot measure things with 26 digits of precision. I'm going to have to at least deal with a small amount of noise, and so it is imperative that the theory be robust against noise. And interestingly, at the end of the previous lecture, somebody came to me and said, you know, what's the relationship between this and Reed-Solomon codes? Are people familiar with Reed-Solomon codes? Because a lot of what I say would be kind of, you know, not known because they don't know about L1 and they don't work over the reals, but, you know, the fact that we can correct errors. You can think about compressed sensing as some kind of an error correcting code, if you will. The thing is that Reed-Solomon and all these kind of error correction codes only deal with binary data, so the worst thing that can happen is a 0 becomes a 1 and you have few errors and you have to deal with this. We have to deal with real life data, and that means that we're going to be subject to noise, and Reed-Solomon, if you try to take it out of its context and port it to real valued signal, will be completely unstable. That cannot deal with noise in any way that I can think of, while the theory will. Okay, so in this lecture we want to discuss robustness vis-a-vis noise. As I said again, and it's so important that I want to repeat it, that if you cannot deal with noise, you should forget it. It's not interesting. Okay, so we've seen two approaches to compressed sensing. The first is probabilistic in nature, where we just sample vectors from a probability distribution, sensing vectors. The other one is kind of deterministic, goes through these restricted isometry properties. Both theory can deal with noise. Okay, so once we have noise, then we cannot really enforce the constraints y equals ax, because y is not equal to ax anymore. So now we observe y equals ax plus z. We know a, but we don't know x and z, and so we want to recover x. Okay, and so z from now on, we're going to take it to be Gaussian. It doesn't have to be even stochastic. It could be deterministic, but for this lecture, mainly I'm going to suppose that the noise is Gaussian. Okay, so one way we could try to solve the recovery problem is to kind of be a bit more relaxed about how we want to fit the data. And so what we could try to do is we could try to find a point that optimizes a certain trade-off. On the one hand, we have fidelity to the data that asks that the fit x hat is close to y. I mean, ax hat is close to y, so this is fidelity to the data. And the other one that it has low complexity in this L1 sense, which is our L1 term. Right, this is a proposal due to Rob Tibshorani. We've seen people in geophysics who are doing this in the 80s, but in statistics it's known as a lasso. Okay, and so a question comes, it's like, how should we so we want to trade off between the goodness of fit and the complexity of the fit, and the question becomes, well, how do you choose lambda? It will be selected wisely. Another noise-aware recovering algorithm is called the Danzig selector that was discussed yesterday, and we're going to assume that the columns of the matrix A are unit norm. If they are not, there is a simple modification to the Danzig selector, which I will just write down, but we're going to assume that the columns are normalized, so let's say they have unit norm. And what the Danzig selector does, it says, well, I'm going to try to find a fit that has minimum sense, a minimum norm in an L1 sense, and is fitting the data. And the way we kind of measure goodness of fit in the Danzig selection is not by an L2 type penalty, but by more like an L infinity penalty, where I'm going to require that the residual vector, what statistician calls the residual vector, that is what is being observed minus what it's fitted, when I hit this residual vector against the matrix A star, that as it, when I look at the correlations between the residuals and the column of A, I want small values. Okay, so this is the form of the Danzig selector. If you don't have normalized columns, what you want is that you want that the vector A star R, the ith component of this vector, be less than the same thing, lambda sigma, but you have to rescale, you have to put the right thing, which is times the norm of the column, the ith column. Okay, so the Danzig selector in its simplest form, when the columns are approximately the same size, the same norm is just simply the infinity norm of A star R is less than lambda sigma. Okay, so it's a bit different from the lasso. I think we had a wonderful explanation of the Danzig selector yesterday. It's a bit different. It's not this. It's not completely unrelated either, but it's not the lasso, and it's slightly different. Of course, it can be recast as a linear program. So it's a linear program, of course. I want to minimize the L1 norm subject to the constraints you see on the board. And of course, I can introduce the slack variables, just like what we did in lecture number 1, where I say, well, let me introduce proxies for slack proxies for the absolute value. So I want to minimize the sum of the ui, subject that x wiggle is between minus u, and I have my L infinity constraint that takes this shape. So I want to minimize the linear function of u and x. Everything is linear, the inequalities are linear, the objective is linear, it's a linear program. And we called it the Danzig selector because when we were actually writing this paper, like we were finishing the paper, George Danzig passed away, and so that's where the name comes from. Okay, so Vincent yesterday kind of motivated very well why this makes sense, and because it did such a good job, I don't feel I have to redo it, so I will skip the motivation. It's basically what you would expect. Is like, okay, we want to find a solution that has minimum L1 norm, but we want also to fit the data, and we want a good fit in the sense that when I look at the residuals, if the residuals were highly correlated with the columns, it means that I should increase the corresponding value, because I don't want to see correlations between the columns of A and the residuals. Otherwise, it means that I don't have the right model. Okay, so Vincent did a very good job, so I'll skip this. Okay. All right, so what results do I have? We're going to be in the setup where we sample from the Fourier transform, or we have random convolutions, or random rows from a random unitary matrix, whatever you want. All right, so we're going to be in the model that we discussed in lecture number 2, the most general model where we just take sensing vectors from a population. Let's say these are, again, frequency measurements to make things completely explicit. So we observe a few Fourier coefficients of a signal that may or may not be sparse, plus some noise. And so what kind of results do we have? So we're not in a regime where we have the restricted isometry property. It does not hold. And so the result that we have is something like this. So we're going to define S to be the point that saturates what we've seen so many times, that M is essentially going to be coherence times S bar times log n. That's a maximum sparsity in a noiseless setting that I could recover anyway. For both the lasso and the Danzig selector, we're going to take lambda to be, let's say, 10 times square root log n. It doesn't have to be that large, but something like square root log n. And as Vincent explained, for the Danzig selector at least, it makes the true vector of unknown, it makes the true x feasible. That is, you're searching in a region that includes the true vector you're trying to recover. Okay, and so the main result says something like this, which is that, the main result, one result says something like this, which is that with very large probability, whether you use a Danzig or the lasso, and we're not in a rip regime here. There's no rip. Like I see k log n Fourier coefficients, and I don't know that the Fourier transform holds up to this level of sparsity. that we have is that we have these kind of error bounds, which are essentially the same that we've seen on Tuesday, except that now we have an extra term which comes from this noise factor. And so in very short order, what this says is that the error that you get is essentially the error you get from the noiseless data, if you had no noise, plus a fraction of the total power. And what fraction of the total power do you get? Well, the fraction depends on the sparsity level. And so if the sparsity is low, you get very little excess of error. So if S is very small, then this term, and sigma is not large, this term is going to be small. Okay, and then as the signal gets less and less complex, then this thing grows. Okay, so in the literature of statistics, this is recognized as a bias variance decomposition, where essentially you have a bias term, which is something like this, which is the error you would get if you had no noise, plus a variance term, which is here proportional to sparsity times sigma squared, times a log factor. Okay, so for practitioners, nothing goes wrong. If basically what I want to convey is that if you can design sensors so that the noise level is not huge, then the error will be small. In fact, the error will likely be dominated by the fact that you just don't get to see a lot of samples and not by the thing. And of course, as the noise level increases, what we have is we have a smooth degradation of the error that you get at very low noise levels as you move to higher noise levels. Okay, but nothing breaks down really, right? So what this is saying, one way of saying this is that the truth in L1 does not lie in the 26 digits of the measurement. All right, so what we're going to try to do in this lecture is understand whether this is a good result and understand whether we could do better. All right. So to do this, I'm going to follow Vincent, and I'm going to talk about oracle and oracle inequalities. So as I grew up in the stats department, well, you know, when you do kind of decision theory, you have the Bayesian framework. So there's Bayesian decision theory, there's minimax decision theory. These are two ways of quantifying the performance of an estimator. And I think as a paradigm, we see a kind of third way of explaining the performance of an estimator, which is Yaz's oracle inequalities, which is what I'm going to explain. Right, and so I view really this framework of oracle inequalities as a very convenient way of explaining how well an estimator does. Okay, so we're going to talk about oracles and oracles inequalities. Okay, so now we're going to assume that we have an oracle, and an oracle, as Vincent says, is there is a genie sitting on the side who has seen X and has decided to reveal very precious information about X. And so this genie who has seen X, in this case, just to make our story a bit simple at the beginning, I have A, I have X, I have Z. And this genie, what it's going to do, it says, you know, I've seen X, X is sparse, and actually it's non-zero in these three coefficients, it's zero everywhere else, and that's the information I'm willing to share. Well, if this is the case, then I claim that we know that Y is a noisy combination of three columns of A. The system is not underdetermined at all anymore. And so if I have that the signal is sparse, if an oracle informs me that, you know, I've seen the support of the signal and this is what it is, then I can have an estimator, which I'm going to call X ideal. And what it does, it just says, okay, now you have a banal least squares problem to solve, because now you don't have to deal with underdetermined systems. You have more measurement than you need, way more measurement than you need. So find the vector which is closest to your data that lives on the support set T that you were kind enough to reveal to me, and is zero outside. Okay, so in statistics we would say that just regress Y onto the variables that you know are in your model. Of course, when I run this least squares problem, I get this, which is a least square solution. So on the support T, x will be simply the least square solution and 0 outside. And now if how well would I be able to do how well would I do with an oracle like this, with very kind to inform me of the support of the code where x is not 0? Well, it's a very simple calculation that the mean squared error, which is simply the expected value of the square distance between x ideal and x. It's a linear estimator in this case. There's a very simple formula. It's the trace of a star t at inverse times sigma squared. But suppose that we are in the good fortune to have a matrix that obeys the restricted isometry property. We know that all the eigenvalues of a star t at are around 1. And so all the eigenvalues here are around 1. And so what I'm doing is I'm just saying, essentially summing 1 s times. And so the mean squared error would be just simply the number of coefficients I'm estimating times sigma squared, which is what everybody in our business knows. Right? So if you have s things to estimate and you have a fairly orthogonal design, then the mean squared error is s times sigma squared. And there's very little surprise about this. The question is, can we do just as well without an oracle? Okay. So just to kind of just explain what, let's suppose that we're in a very simple case where A is the identity. So it's not even undersampled now. What we see is we just see direct observation. So I see yi equals xi plus di. Okay, there's no undersampling here. What statisticians would say, what is my estimate of x? Well, it's going to be the maximum likelihood estimate, which in this case is simply y. And the mean squared error of y would be, of course, the number of coordinates times sigma squared, so it would be n sigma squared. But if the signal x is sparse, just like as we've seen, and if I have an oracle that tells me, well, look, I tell you which coefficients are zeros and which are not, then you would set to 0 almost all the coordinates but a few. And of course, you would pay a mean squared error, which is s times sigma squared. And so, of course, the mean squared error, if I have an oracle, can be much lower than what I would do naively without an oracle. Okay, so when the unknown vector is sparse, it's much, I should use the oracle, and I'm going to reduce the mean squared error by a tremendous amount. All right, so one easy result is that if we have a matrix A which obeys this restricted isometry property, all right, and if the restricted isometry constant is exactly what it used to be in the noiseless case, in fact, I think we've seen that we could push it to 0.46, if I remember, so it would also hold with that value of the constant. And if I'm sensing a vector that is S sparse, then I can get to within a log factor of what I would get with an oracle that is actually revealing the support. Because if I have an oracle that reveals the support, the mean squared error is going to be S times sigma squared. I have an oracle. I don't have an oracle. I just solved my Danzig selector problem. Okay, so this is the solution to the Danzig. So I'm sorry, I did not make this precise. The solution to the Danzig selector will have a squared distance, which is within a logarithmic factor of what is achievable with an oracle.
What's large probability being exactly here? So not the case when what is larger?
Okay, so it's a probability. Now the matrix is deterministic because we have this condition, right? And so probability, it's a probability over the noise. So it's what Vincent explained yesterday, is that what's the probability that essentially the probability of failure is the probability that your constraints in the Danzig selector is violated. Okay, it's probability that X is not feasible for your problem, but you set lambda to be large enough so with overwhelming probability X is in your search region. Okay. All right. So what's interesting about this result is that the mean squared error is proportional to the true unknown number of parameters. So of course, the Danzig selection does not know how many non-zero coefficients there are. All what it does, it solves this. So there's no S in this formulation, just solves a linear program, not knowing what S is. and what it outputs a mean squared error, which is proportional to the true complexity of the signal, and that's what we call in statistics adaptivity. That is, your mean squared error adapts itself to the complexity of the object. When the object is very sparse, you have a small mean squared error, and when it's not that sparse, it increases. All right, and then as Vincent discussed yesterday, what is this log n factor? Essentially, the price to pay for not knowing where the coefficients, the significant coordinates are ahead of time. Right? You're going to have to pay a price with vis-a-vis an oracle, because what you don't have to do is you don't have to do what is common now in statistics. You don't have to do multiple hypothesis testing. You don't have to find those locations where the signal is non-zero. Okay, and when you do have to find them, you've got this log. Okay. In a way, there's an analogy with information theory, which is, you know, how many bits does it cost you to encode an amplitude? Well, let's say it costs me 8 bits. How many bits does it cost you to encode a spike in a length n? Well, it's not going to cost you 8 bits because you have to tell me where this spike is going to be, and for this you're going to pay log n bits. And there's an analogy between this, what I just said, and this log factor. Okay, so the geometry of why this work is kind of always the same. It's not surprising anymore. It's the reason why you get accurate estimation is because of this pointiness of the L1 ball in high dimensions. And so now, before, when we were noiseless, we were taking this measurement, and so we were looking for an L1 minimum over this line, and so we were exactly getting our sparse guy, which is somewhere here. Now we're not noiseless anymore, we have noise, so there is an uncertainty around this line. In fact, in high dimension, there's this uncertainty around this whole null space, which is huge. But so we have a big null space, which is here, and there is an uncertainty in the measurements you're taking. So there's a whole slab that you know that the solution in this is slab, but you don't know where in this slab. Okay, so what the measurement gives you in the noiseless case is you know you're on a plane, and when we have noise, it's a bit different. So we know that we're in a slab. Okay, so that's information number one. The fact that we have noise means that we're not exactly on this plane, but we know that we're in this slab. And fact two is, well, but what if I was making sure that my solution x, the true x, is feasible for the optimization problem, right? So if x is feasible for the optimization problem, the Danzig solution will have a L1 norm which is less than the true L1 norm. And so if this is my true x, then I know that x hat will be also in the L1 ball here, right? So what I know out of these two things is that if my fit problem is feasible, then I know that the solution that the Danzig will return is in this L1 ball, which summits at x, and I also know it's in this slab. So it must be in this shaded region that we see here. But because the restricted isometry enforces that what the restricted isometry property does, it says that, well, but you know this null space of A cannot be tangent to this L1 ball. It's actually quite orthogonal to it. And therefore, the radius of this area is not big, and any point in that region will be a very accurate estimate. Okay? And the Danzig selector happens to find in that region the point with minimum L1 norm, so we'd actually find this guy, and what it would do, it would just do self-thresholding, essentially, something like that. So it would slightly underestimate the value x. Right? But basically, the geometry is very clear. It's because the null space of A is kind of orthogonal to the low-dimensional face of the L1 ball that recovery from noisy data is possible. Okay, so we've got this, which is nice. So let me go back to my oracle. My oracle informs me of the support T, and then I just do least squares, and so I get S times sigma squared. But is this a good oracle? So the question I want to say is, well, is this good information, or maybe the oracle did not reveal enough about the problem And so I want to kind of talk about a more powerful oracle now. So let's talk about better oracles. So we're going to be in the easy case where A is the identity, so we observe xi plus di. But now the oracle tells me more precise information. It actually tells me which coordinates are above the noise level and which coordinates are below. So it actually tells me which coordinates are above sigma and which coordinates are below. And that's kind of better. That's a better oracle because if I have this information, I could decide, once I know the coordinate is below the noise level, there's not really a lot of information in that in y to estimate this reliably, so I will just set it to 0. And when it's above the noise level, I will set it to y. Okay, so once I've got the side information about which coordinates are worth estimating and which coordinates are not worth estimating, I go through this very simple procedure, which is if the coefficient is small, there is no point in trying to estimate it, so I'm just going to declare that my estimate is 0. If it's above the noise level, then I should try to estimate it, and I'm just going to use y, since this will be an unbiased estimate of xi. Okay, so what the MSC, what the mean squared error is ideal estimator, well, we see that there were two cases. Either xi is below the noise level, and in this case, I'm going to pay xi squared. I'm going to make an error which is xi squared, or xi is truly above the noise level. In this case, I'm going to pay the variance term. I'm going to pay the variance of yi, which is sigma squared, so I'm going to pay the minimum. Right? And that's better than what we had before, because before we were just paying the sum of the sigma squared. But now we pay the minimum, because if some coefficients are very low, I should not try to estimate. I'm going to pay a huge price in terms of variance. And so what this is kind of the optimal bias variance trade-off, which is if the coefficients are small, pay the bias and do not pay the variance, because the bias is below the variance. If they're above the standard deviation, pay the variance, not the bias. And so this is really an optimal bias variance trade-off where you're going to pay the minimum between these two things. And of course, it relies on an oracle that tells me very precisely whether coordinates are worth estimating or not. Another formulation, which is consistent with what we've been discussing all along, is that you can rewrite this expression as an approximation error, which is the distance between x and its best s-sparse approximation, plus s times sigma squared. So when you look at this, it's going to be the number of coefficients above sigma squared times sigma squared plus the rest. And one way to rewrite this quantity is to recognize that this is a distance between x and its vector of largest coefficients plus s times sigma squared. And what the oracle says, it says, I've seen x, so I let you pick the minimum s, so I let you choose the best trade-off between the approximation error that you get by only estimating s coefficients and the variance you get, which is s times sigma squared. All right, so that's what the oracle does. And so we can see that this can be much smaller than s times sigma squared, because if for example, let's say that we have lots of xi's, but they're all very small, then there's no reason I should pay s sigma squared. I should just pay 0. A different perspective on the same problem is something like this. And that's the way oracle inequalities are cast usually in the literature, is something like this. What I'm going to do is I'm going to go through a combinatorial enumeration of all possible subsets of coordinates. So for all possible subsets of coordinate I, I'm going to pretend that I have signal on I and no signal on I complement. Okay, that's what I'm going to do. And for all possible subsets of 1 through n, I'm going to construct this estimator that estimates over I and does not estimate over I complement. And so when I look at the performance of these estimators, it will of course be, when you declare it's 0, when it's xi, you would pay the sum of xi squared over the complement. For each term in I, you pay a variance term, which is sigma squared, so you would get this error. Okay. And now, the way we people cast oracle inequalities is say, now I have exponentially many estimators, because I have exponentially many subsets to choose from. And the oracle who has seen the truth is actually revealing to me the best subset. All right? And so what it does, what the oracle says, it says, you know, I've seen the truth X. I know which subset you should choose for estimation. You should use that one. And so it's minimizing over all possible, over these exponentially many estimators, is minimizing the mean squared error. All right? And it's not hard to show that, of course, the estimator we introduced before that just decides to estimate or not, depending on whether xi is above sigma or not, is exactly that estimator. And its performance is what we've seen already, right? So the way you minimize this is by setting, by choosing I to be significant, by choosing the set if xi is above sigma, xi squared is above sigma squared, and setting it to 0 otherwise, which is what we had before. Okay, so what the way people try to kind of compare performance of estimators is, here I have a lot of realistic estimators. I'm going to fit all possible least squares problems, assuming all possible supports. The oracle knows which one is best, and what I want to do is I want to compare with that. Now, in the case of sparse regression, this is exactly the same story. Now, A does not have to be in the identity for my little story. What I have is I'm going to look at all possible subsets of coordinates that could potentially be significant. And I'm going to look at all these exponentially many subsets. Then I'm going to use a least squares estimate pretending that the signal is significant over these coordinates. And the oracle, which knows which subset is best, will be able to give me the best least squares estimate in this family, which is simply minimizing the mean squared error over all possible choices of subsets. Right? What I claim is if we have a restricted isometry property, the expected value of x minus x star squared is exactly what we had before. So whether A is the identity or not, it doesn't change. In this context, the mean squared error is the sum of xi squared sigma squared, the sum of the minimum between xi squared and sigma squared. Okay? And the question is, can we achieve this ideal rate? So of course, this is smaller than s times sigma squared, because if there are lots of xi that are very small, then this quantity will be much smaller than the number of non-zero coefficients times sigma squared. Okay, so how do you get calculations like this? Maybe I'll skip this. You use the fact that over sparse subsets of columns, you know, AI star AI is well conditioned, so the trace is essentially the number, the dimension of I, and so what you get is you invoke the restricted isometry property to show that, well, because subsets of columns of AI are well conditioned with eigenvalues around 1, then essentially you get this. Okay. And so the more subtle version of the Danzig selection says that we're going to assume, we're going to make the same assumption as before. We're going to assume that x is S sparse, and with very large probability in exactly the same sense as before. Then what you guaranteed is that the error that you pay by invoking the Danzig selector is within a log factor, which we explain why we need this log factor, times sigma squared plus the error that the ideal estimator would do. So you within a log factor of what is possible with an oracle that you have fitted all possible subsets. The oracle knows which one is best. Then what you guaranteed is you're guaranteed to fall within a log factor of this. Okay, and you can extend this to non-sparse vector x. And so what it says is that not knowing anything, you can mimic the performance to within logarithmic factor of what is achievable with an oracle. Okay, there are some people, they say, oh, you know, you have log n, and log n really is going to multiply the ideal mean squared error. The ideal mean squared error is the mean of sum of xi s squared. And they say, I can get a better result because the log really multiplies sigma squared and not xi squared. So it multiplies the variance term, not the bias term. And in fact, if you look at the paper, that's what is established. Okay, so really the log factor, if you want to be very precise, multiplies the variance term, but not the bias term. Okay. All All right. So in some sense, this was a starting point for lots of research in statistics. And so now there's a lot of papers in statistics about L1 theory for sparse regression. So for example, in this important paper, Bickel, Ritov, and Sibakov kind of got slightly stronger result for the Danzig selector. Tong Jiang extended the result to show that they're also true for the lasso. There's really an explosion of papers in the literature on statistics to actually understand once sparse recovery from noisy data is possible. I tried to list a lot of papers I've read. There are many, many others. I'm sure I'm forgetting lots of people, but there's really an exploding theory in the field, and a lot of people contribute very, very good ideas. More recently, we had a talk yesterday by Vincent. This is a field that is really growing very fast, with lots of extraordinary people contributing, and so we know more and more and more about these problems, and probably much more than what you see here. Okay, so again, many people contribute. So these two papers are kind of important because they say that what we prove for the Danzig is also true for the lasso. Okay, and H1 we have our own assumptions. Things change a bit, but knowledge is increasing at a fast rate. Okay. There are other works that go in slightly different direction. My colleague Andrea Montanari is looking at other algorithms for sparse regression, something we call AMP, and there are very detailed studies about the performance of these algorithms in settings where the matrix A here is IID Gaussian. Okay, so you don't have to use L1 all the time, just like as we've seen for noiseless recovery, I showed you COSAMP. And there are message passing algorithms that could do in some settings where all the matrix A is Gaussian that would do well as well. And so Montanari is a leading figure in this area. And recently there was an interesting paper by Montanari, Donahoe, Johnson, and Bayati about the minimax calculations when A is Gaussian. And so they get very precise results. Okay, so again, lots of theories. People use L1, people use other algorithms, and so we learn more and more about what is true and what is not true. Okay, so in practice, maybe I'll show you again a little demo just like this morning. In practice, if this works this time. Okay, so I'll show you a little demo. Okay, so we're going to make a matrix which has 256 rows, 512 columns. It's a Gaussian matrix which is normalized. And we're going to make a sparse X. We're going to add noise to it. And we're going to compute AX plus noise. And we're going to make Y, which is AX plus noise. And that's what this is doing. Okay, and now we're going to solve the Danzig problem. So in MATLAB, this is, at least using CVX, which you've seen this morning, is very, very simple. I'm going to minimize the L1 norm of X subject to A star times Y minus AX is less than lambda sigma times those column norms that I calculated. And if I'm lucky, something should be running. So we see that it solves this linear program. All right, and we see that we kind of do well. Of course, it's not perfect because now I have noise. And what do we see? We see that most of the time, so again, this comment from this morning, that why do I only see the red? Because the red is on top of the blue. And we see that whenever the coefficients are not zero, we kind of predict that they are not zero, but we tend to underestimate their value. That's a typical feature of L1 regression. I think Vincent explained very well yesterday that if A is orthogonal, then it is thresholding, soft thresholding, so you lower you diminish the contrast, so you tend to underestimate the value of the coefficients. And see, I think here I'm plotting the absolute value versus the recovered absolute value. That's why everything is positive. Also, in the Gaussian case, it doesn't matter because since my matrix A is Gaussian, whether it's positive or negative does not make any difference. But okay, and so what we see is we have a tendency to, okay, so we kind of do well, but we have a tendency to underestimate the true values, which is well known for L1 methods. And so what one can do in this setup is we can use a two-step procedure. What we're going to do in MATLAB is we're going to invoke this common find. We're going to see where is our guess above the noise level. And then we're just going to do least squares. So that's going to be my estimated support. And then I'm going to do least squares on it. Okay, so I'm going to find those recovered x which exceed the noise level. I'm going to declare that these x's are not 0. And then I'm just going to run least squares on this. Right, so this is a debiasing step. You can do it in different ways, but that's one way of doing it. All right. Of course, when you do this, you make mistakes because you don't really guess. You don't really have not guessed the support completely accurately, but that's your debiasing step. So you have in blue the original signal, in red the recovered signal, and what you see is now that the observations seem to be more centered around the blue points, and that's removing the downward bias that these L1 methods are associated with. You could also do this by reweighting if you wanted to. So this morning we saw reweighting. And so now that you've got an estimate x hat, what you could do is you could create with those weights wi, which are 1 over xi hat, plus something that might be like something like the standard deviation, why not, or a multiple of the standard deviation. Okay, so you could create weights like this, and then next time around you solve a weighted program. And so this will do is that it will remove the bias. It will, it does not penalize for large amplitude, so it would debias the estimate, and that would be something that looks like hard thresholding now instead of soft threshold. Okay, so there are many ways you could do this. One way is by trying to identify a reasonable support and fit least squares, and one is by just running one iteration of reweighting or a few. All right, so this we kind of seen because we kind of run it on the computer. Okay, and so you can. It's really a simple thing. You run your L1 procedure to determine which coordinates are likely to be significant, and then you construct the least squares estimate on this subset of columns. Any questions? Yeah.
Something that bothers me about compressed sensing is we assume that our signal is sparse in some domain.
Yeah.
But we also assume that every entry which is not sparse with a vector belongs to a real numbers or complex numbers. Now my question is, would it help in denoising if we would know that every entry belongs to some discrete set? So the correct value is discrete in values. Does it help somehow?
Yeah, I mean, the more prior you have, the better. The more prior knowledge you have, the better. Yeah, I mean, I suppose it would. I mean, you can you can try to incorporate what you just said into constraints. Of course, the challenge becomes, can you make them convex in some ways, right? So if you could play around with your idea and say, because what we don't want is we don't want to have intractable problems all of a sudden, right? But if there's a way to incorporate your ideas into convex constraints, then yes, that would improve, I think. Okay, in practice, the ratio between the oracle risk and what you get by Zerdantic selection is quite small. I think you've seen an example across large values of sparsity, something like 4 or 5, so you don't do much worse than an oracle. And this is on data with 5,000 unknowns, 1,000 equations. You see the parameters. I mean, what we see is essentially that the oracle ratio is in practice not too crazy. So this is an example, a large-scale example, where we've got 5,000 unknowns, of which we can only get to see 1,000 equations, and we solve this Danzig, and we do well. And if we look at the first 500 coordinates, we do well, but maybe because the noise level is not very high, that's why we do well, probably. Okay, so you can do this on images. So this is my phantom that we still cannot see after 3 days. All right, so this is kind of interesting, because this now the data are Fourier data on this example. So I'm sampling the Fourier transform along radial lines. I have very few radial lines, I have very few samples. It's an example where the number of equations is roughly 4% of the number of pixels. So 96% of the equations are missing, as we discussed in the first lecture. Because the Fourier transform is rapidly decaying, a lot of the Fourier samples along a radial line will actually fall below. So the red line is the noise level, and these blue dots are the true value of the Fourier transform, and they completely buried in noise very quickly because they're small, because Fourier high frequency coefficients are small, and so they are kind of most, after Fourier coefficient number 40, everything is kind of below the noise level. They have only a few low frequency coefficients that are significantly above the noise level. All right, okay, so we have quite a significant amount of noise for compressed sensing experiment, but because this object is so sparse, maybe there is hope. And sure enough, if you minimize the L1 norm of the gradient and you recover the phantom, you will get this wonderful picture you see on the top right. And here I'm fortunate that I thought about plotting the level lines of the recovered object. So what you've got is a line going through the middle of the phantom with its intensity as you're moving from left to right, roughly halfway. And in blue you see the original signal, and in red you see the recovered signal. And so you see that you do a very good job at recovering these things, and this is not really surprising, because even though you have very few measurements, you're dealing with a sparse object. The Fourier transform is nice, and so you're in a good situation. That's what the same level line that what people use in medical imaging would use, which is a filter back projection, and you see that, of course, the recovered line of a phantom looks nothing like what it should. Okay, so in practice, people report good performance. So whether you use the Danzig or the Lasso, they're all good. They're pretty much the same practically, so they're both perfectly fine. Here's another experiment which we'll talk a bit about more on Friday, which is that now we're going to have a signal which we're going to observe at few. I think that's a discussion we had also, and that's what I thought about including this for discussion. So for discussion is that we have a signal that is sparse in the Fourier domain. So now we have a signal that has a sparse spectrum. So maybe I'll show you the signal in the Fourier domain. Okay, so that's a signal in time, but in fact its spectrum is quite sparse, which is what you see on the right here. So it's a sparse signal in the Fourier domain, and I'm going to decide to sample it in time. So we're going to use a device, which is what we kind of talked about in the discussion at the end of the last lecture, where I'm not going to sample uniformly in time, I'm going to sample non-uniformly in time, right? So instead of sampling at this very high Nyquist rate that we see over there, I'm going to sample just at a very low rate, but non-uniformly. Okay, and so now I have exactly the setup of the Fourier type measurement, because the inverse Fourier transform and the forward Fourier transform are the same objects. So I should be able to do well. That is, if I take a number of time samples with essentially at least 4 times the number of significant frequencies, I should be roughly in business. Okay, and so when you run numbers, you'll see that you're roughly in business. And so how do you communicate with engineers something like this? You say, well, you have very few time samples, but suppose you had seen them all, then how well could you do? Well, you could invert the Fourier transform, zero out the Fourier transform when there's no energy, invert the Fourier transform, get an accurate estimate. Of course, you don't get to see all the samples, and nobody tells you which which Fourier modes are active and which are not. But when you run either the lasso or the Dandick selector, it doesn't really seem to matter because it will get a mean squared error, which is essentially S times sigma squared, the number of significant coefficients times the noise level. In this experiment is 115, and I think the constant is very low because all the frequency components are strong enough so that they clearly stand above the noise level, and therefore when we go through this debiasing procedure, we pay essentially sigma squared. Okay, so what it says is that, if we were thinking about engineering applications of these ideas where we have a communications system that is, its goal is to surveil a wide band, but we cannot sample at the Nyquist rate. What this is saying is that if we could perhaps sample at a reduced Nyquist rate by tweaking the clock of this ADC, and if we were to observe signals that had some sparsity in the frequency domain, then that should be okay. Even though, of course, the digitizer, the machine that is actually sampling the data, digitizing the data, would come with errors. Okay. All right. Sure.
Is the interval between the time sample that you do, is it important that it's incommensurate with the frequency you're looking at?
No, it just have to be random.
It has.
Well, what I can say is that if I take random time samples, if I have a random generator that decides which time point I'm going to choose, almost all choices are going to be good, and a tiny fraction will not be good. Now, if you show me a pattern, can I tell you it's good? No. That's always a problem we've been discussing for a while now.
So in short, by taking a random samples, you're increasing the RIP. I mean, you're making better, or not.
By what?
By taking random samples instead of taking uniform, you are creating better restricted isometric property. Can we say so, or do I understand correctly?
Yeah, I mean, what I'm saying is that if I randomly sample things with very high probability, I'm going to obey RIP. What I cannot say is, are these subsample rows, do they obey RIP? This I can't answer, unfortunately. But I know that almost all subsets of sampled rows will obey RIP.
Even though you randomize the clock of ADC to take those random samples, you need to know the exact timings
Of course.
when you're taking it.
That's where the noise comes in, because you have time jitter.
Yeah, exactly.
Of course. I spent half of my life in these things, so I know all about. Yeah. Okay. So go ahead.
Isn't it a way better solution to use this so-called random demodulation, so multiply the signal by some kind of
Yeah, but then I can say, at what precision can you randomly modulate the signal? Isn't it the same issue? Because if I say you can change the polarity of a frequency wave at a very high rate, do you think you can really do it? You think you can, but you cannot, right? So what you're saying is, I think we'll talk about this on Friday, all of this. But it's interesting that these questions come up early, is that I think what you're referring to is that perhaps what I should do is I should try to multiply the signal by random sequence of plus and minus ones, and then integrate or do something like that.
Yeah, exactly.
But the thing is, do you think you can do this? Because you're going to have the same issue. You think you're transitioning between plus one and minus one, but in fact you're doing this. And you have a lot of uncertainty about, I cannot change the polarity instantly at an incredibly high precision. I can't do that. So, in these random mixing schemes, you're going to have to deal with not exactly this kind of uncertainty, but a uncertainty of very similar, right? And so, what is exactly your circuits doing at that speed? We don't know. That's why we spend half of our life calibrating things. And yeah. But these are very good issues. And that's why it's very important for compressed sensing to be robust vis-a-vis all these kind of non-ideal ideas, because if compressed sensing required extraordinarily precise knowledge of the rows of A, then there's no way I know what the system is doing with infinite accuracy anyway. Right. So I can model the uncertainty as I have about what the system is actually measuring as something like an additive error. Okay. The same is true for the Fourier things, the MR example, where in the noise term of the MR, there's, of course, the electronics of the machine, the person moving, and also the fact that it's not true that the measurement of the Fourier transform of something. It's just an approximation. Right? So there's lots of things that go into these noise terms. There are things modeling that what you don't know about this. There are things modeling the fact that we only have approximate equations from physics. There's lots of things.
Just a question about doing this in on a computer. You use a random number generator.
Yes.
What happens if you use a bad random number generator?
I never saw something go bad.
It's not.
No. In fact, what's surprising and what surprises people is that whether you do experiments with Gaussians, binary, even Fourier, the behavior is so stable. Even though I don't have a random generator, even though I'm a lot of types of measurement ensemble give you exactly the same performance. So, other questions? But it's not surprising, so we know that most of them works. Yeah.
The results that you showed so far in this lecture, they do not depend on the parameter lambda, but the estimate of the dancing and the lasso estimate, they depend on a parameter.
Yeah.
So does this mean that independent of what value of the parameter I choose, I have...
No, if lambda is chosen too small, you're going to get disastrous results.
But this doesn't come in the results.
Well, it comes because there's an assumption. Okay. I said lambda needs to be something like square root log n. If I take lambda smaller than this, things will break down.
Does not depend on sigma squared.
Okay, so the way I set these are all good questions. The way I set the density constraints is by multiplying by sigma in specific. So lambda is simply,
Assume it's no.
assume it's not.
So you have actually recipe how to choose lambda.
We have theoretical recipes, which we know that it has to be on the order of square root log n. In practice, we don't choose this, we choose something a bit smaller. It's too conservative, but that's what the theory wants. But it's a bit too conservative. It tends to kill too much signal. So what you try to do is try to find adaptively a good lambda that you like, by cross-validation and things like that. All right, so okay, how good of a result can we get? I just show this for, I don't know, for those of you who are interested in these things. If I don't want to be universally good, but I want to be, I decided X is fixed, I take A to be Gaussian, you can really achieve the optimal bias variance trade-off. That is, that you have the result that is the cleanest that I can think of, which is that the distance between X and X is truly the square distance between X and XS times the log factor times S sigma squared. And that, for this to hold, you need the RIP and something else. This something else was proposed by Wojciech a few years ago. And if you assume that's something else, then you can really get what you might want to call the ultimate result, because this is the oracle error, where the log just multiplies the variance term, everything is the same, and so you're really matching the oracle very precisely. But it's not universal. So this is only true holds for a fixed X, and it cannot hold universally. In fact, it's known that this cannot hold. A bound like this cannot hold for all X, simply because when sigma is getting close to 0, it would say, can I actually have instance optimality in the L2 norm? And that is known not to hold. So it's true for fixed x. Arbitrary, but fixed. Okay, so we talked a lot about stochastic noise. What if we have deterministic noise? What if I'm not willing to assume that the noise is stochastic? And so perhaps I have a bounded perturbation now. So I have y equals ax plus z. I'm going to assume that the norm of z is less than epsilon in some L2 sense, for example. And then in that case, I'm going to minimize the L1 norm subject to the distance between the recovery and the fit and the data is less than the noise power, the noise power epsilon squared. Okay, so now I'm not making any assumption about stochasticity in the noise. I'm just saying, z could be absolutely adversarial, but it has bounded power. And by a bound that I kind of know, which we're going to call epsilon squared. And if we do this, then again, if this restricted isometry property holds, then you can show that the distance between the recovery and the truth is what you would get in the noiseless world plus the size of the noise. Okay, so the situation is very simple. You get what you would get if you had no noise plus the noise level. Okay, so you don't have to have stochastic noise. What's nice about stochastic noise is that you can get stronger result, because in the stochastic noise, epsilon for stochastic would be simply the number of measurements times sigma squared. So, if z is Gaussian, but I don't know this and I assume it's adversarial, so the norm of z squared would be roughly m times sigma squared. And so what do we say that, if say z is 0, if we have sparse vectors, that the squared error would be proportional to the number of measurements times sigma squared, whereas what we've seen is proportional to s times sigma squared, which is adaptive, while this is not. But if you're not willing to make stochastic assumptions, and if I can choose any z anywhere I want in the ball of radius epsilon, then I don't think you can do significantly better than this. All right, so all the theory seems to be very robust. It's very robust to impulse noise. We've seen this morning. It's robust to stochastic noise. It's robust to deterministic noise, and that's what makes it applicable in real life. Now, I want to spend 5 minutes discussing ultimate limits of performance and be a bit provocative in the last few minutes. Okay. So what is the theme of this lecture? The theme of this lecture is that we're going to acquire information about the vectors, a sparse vector x by random sensing. Okay, and the way we do it in a typical example is I'm going to take AK, which are independent copy of white noise. So the rows of my matrix X are white noise, which means 0 variance 1 over n. I normalize things this way so that each row in the matrix has norm roughly 1. So we're making these measurements. Okay, so we have our matrix, we assemble equations. Right, and so of course the norm of AK squared is going to be n times the variance, which is 1 over n, so it's 1. So if I normalize things this way, the rows are kind of unit normed. So that's just a convenient way to say that I'm dealing with unit norm rows. I'm going to perform L1 recovery. And what we've seen is that for all sparse vectors, we can essentially guarantee S times sigma squared error. And so if I use this normalization instead, when you use RIP arguments, essentially we're changing the things. RIP would say that to have all the eigenvalues of this matrix close to 1, the normalization would need to be a bit different. Instead of having variance 1 over n, they would have to have variance m over n, so that now the columns have norm roughly 1. But if I take this special normalization, okay, so of course all the results we scale, and what the result says, the results say that the distance between x hat and x squared per coordinate is roughly s times sigma squared times log n, that's what we've seen, divided by m. Okay, so that's kind of what the result says, or in other words, x hat minus x squared is n over m times s times sigma squared times log n, and this n over m comes from the fact that we normalize things differently. And we know that this error holds as soon as the rip holds, and so for Gaussian, we know that the rip holds at level s log n over s. All right, and now I want to ask the question we asked yesterday, which is it possible to do better by using a completely different sensing mechanism and by using a much smarter algorithm for recovery? And now the question is wide-ranging, because now you can use any sensing matrix you like. So not only you can question about compressed sensing L1, but you can also question the data acquisition process itself. Okay, there's something troubling about compressed sensing that not many people discuss, and I'm going to tell you what this is. There are two facts about compressed sensing. One that we heard in Mark's lecture, which is that we lose 3 dB per octave. And what does this mean, to lose 3 dB per octave? It means that the mean squared error, which we've seen is n over m times s times sigma squared, or maybe if I normalize it by 1 over m, so that the mean squared error per entry, which is m times n, 1 over m times s times sigma squared, if I decrease the number of measurements, then this gets worse. And engineers think about this as that's a 3 dB loss. That is, if m per octave, if m is reduced by a factor 2, then the mean squared error increases by a factor 2, and that's your 3 dB loss. And that's true, because as you get more and more data, estimates are less accurate. And what I've learned as a child is that averages are more accurate than individual observations. And of course, if I reduce the number of observations, m, then I'm not going to be as accurate. And what that means is that each time I reduce the number of measurements by a factor 2, I lose accuracy. And how much accuracy on a dB scale? 3 dB. Okay. That's not troubling. That's just statistics. Averages are more accurate than individual observations. What is troubling, though, is this, which I don't see being discussed very much, is that the incoherent measurements seem to capture very little energy about the signal of interest. Because by design, these random sensing waveforms are orthogonal to the signal. And it has to trouble you. They don't capture much energy. In each measurement, there is very low signal power. Because if we take these Gaussian measurements, A will be by design orthogonal to the signal. Right? If I take a fixed x and I take a Gaussian random vector, it will be orthogonal to it. And therefore, when I compute my dot product, ak.x, it's very small. It's very small because A and x are orthogonal to each other. And personally, this troubles me a lot, that somehow this compressed acquisition protocol is getting you the right information, but it gives you at a price. And the price is that you lose a lot of signal power. Right? Because you have one x pointing in one direction, you have one A pointing in almost orthogonal direction, and then you make the inner product, and of course you destroy a lot of the signal. And so compressed sensing measurements yields low SNR measurements. And that's not very good. Any remark about this?
For applications that typically deal with very noisy data, the signal to noise is crucial.
Yeah.
Are you aware of successful implementation of compressed
Yeah. Yeah, and I'll show some Friday. But I think fundamentally this is trouble. That somehow we use this incoherence waveform. Why do we use incoherence? Because we need to cast a wide net. If we don't cast a wide net, sparse signal might slip through the cracks. But by casting this wide net, implicitly what we're doing is we're sacrificing signal-to-noise ratio. And that's why this lecture about noise is so important, because it's very important to understand the relationship between signal power and noise power. Yes, we're incoherent, but the price we pay for incoherence is that the measurements actually have very little information about X. They have some, but it's kind of at a very low level. Okay, so here is what we could say. We say, so that's why sometimes there's something that I find a bit unsettling about all of this. But I also know this, which is that, all right, so maybe it's not a good idea. So you see, this is why you really want to question this sensing by random acquisition, which is that maybe this is a bad idea. Maybe to actually use incoherent waveforms in a noiseless case, there's no problem with it. But as we have noise, we leave so much signal-to-noise ratio that maybe it's a bad idea. So you could question two things. I gave you weapons to actually question the sensing mechanism itself. And of course, you could question L1. Okay, so, but the situation is not as bad as what it seems. Because what I could say is, I say, well, maybe we don't believe all of what I'm telling you, which is we don't believe that random sensing is good. We don't believe that L1 is good. We believe nothing of it because maybe we're smarter and we know how to make a better sensing matrix. Maybe non-random, deterministic. We know how to make it. So what I'm going to let you do is I'm going to choose any A you like. Of course, I want to control the signal-to-noise ratio, so that I'm going to input a power constraint on A. And what I mean is that the sum of squares of the entries of your matrix is at most m, so that roughly the energy per row is 1, which is what we've got in this naive Gaussian case. Right, so we have, I'm going to use your A. Of course, if you can multiply A by 20 million, all these problems disappear because the signal-to-noise ratio will be enormous. Okay, but let's say that we have on one hand, we have the Gaussian sensing where we sense by white noise, and on the right hand, we have you who knows better, and what you say is, well, but I know which sensing mechanism to use. I'm going to respect your power constraint, but I'm going to pick the best one I can. And also, you don't like L1, and so you're going to use maybe something that's combinatorially hard, any recovery algorithm you like to recover. And the result is that you would not do better. If you can pick any A you like, and any recovery algorithm you like, then the mean squared error you'll get at the end of the day is the error that you get from CS measurements. And in fact, it's very, very close. You get that the mean squared error, so we had S times sigma squared times log n with a Danzig selector and random Gaussian measurements. And if you can pick any A you like with respect to this power constraint, any recovery algorithm whatsoever, then you cannot do better than that. Okay?
The recovery algorithm is A times X.
No, the recovery algorithm is anything you want. What you observe is AX plus Z. The input data is AX plus Z. You can choose A. Now A has to be linear. You choose your sensing vectors, you measure AX, you add noise to it, and what I'm saying is however you decide to choose your matrix A under these power constraints, and however you decide to recover the sparse signal, maybe not using L1, maybe using any algorithm you can think of, the mean squared error that you will pay is S times sigma squared over n times log n over S. And the only difference between what we have here is that, we don't have log n over S, we have log n. And so yes, it's strange that yes, you build these measurements that are orthogonal. Yes, you lose a lot of signal power, but if you have a power constraint budget, then at least this theory says, in some minimax sense, that you cannot find a sensing mechanism and an algorithm or pair of a sensing mechanism plus an algorithm that would achieve a lower MSE in a minimax sense. Okay. So that's why I'm not completely depressed. All right, there's related work. So this is a recent result due to myself and Mark Davenport from Stanford. There's a related result by Raskuti, Wainwright, and Yu, where they prove a result like this, but they restrict the choice to matrices obeying the restricted isometry property, which, well, that's the thing I'm challenging. Maybe that's a bad idea, this restricted isometry property. So there's a related work by these three guys. They have two papers, actually. One that studies A's that have IID entries, but that's, again, what we're trying to challenge here, and one where A obeys the restricted isometry property, and they get a similar bound. But what I'm trying to say is, what if you don't believe in the restricted isometry? What if you don't believe in random designs? Then what? What's funny is that a key proof for this is the operator Bernstein inequality we've seen this morning, which, of course, it comes deep in the proof, but
So the theorem holds for any s less than or equal to n, or?
it holds all the time.
Actually, if s is larger than n, then just log here. Negative.
Yeah, so maybe plus. Maybe I should add +1 or something like that. I'm sorry for being a bit sloppy. Yeah. But S cannot really be larger than n since n is fixed.
Yeah,
Right. So it's your S bar signal.
No, sure.
Yeah. So I think it's actually correct the way it is, except that I probably forgot +1. So it's going to be log n over S plus 1 times S sigma squared over n. Okay. Yeah.
No discussion?
Yeah. It doesn't have to be really, but let's. Well, no, our proof works with Gaussian noise. Yes. In fact, we know. Well, yeah, Gaussian noise. Okay, so no matrix will do better. I can prove some results, but maybe not. Okay, so what we've seen is that we could have accurate estimation from few observations. It's possible. We need to solve an LP or a second order Kohn program. So an LP if we're dealing with a Danzig selector, a second order Kohn program if we deal with a lasso. We need an incoherent design to guarantee good error bounds. There are many opportunities because now all of a sudden the fact that you have robustness vis-a-vis noise makes it deployable in applications, and some of them we'll discuss soon. Thank you.
Well, it's certainly time for a question or two, if anyone has one.
One that we maybe touched upon briefly yesterday, which is a little provocative, but so all these oracle inequalities, they tell you your estimator is sort of very good, but as in other instances so far, you don't really know how good it is when you use the estimator. So say if I come up with just this silly hypothesis that x actually is 0, can you design a test to reject or accept this hypothesis in the end and give critical regions, or do we just have to look at the scatter plot and sort of be intuitive?
Yeah, I mean, I think now, in general, I think your question is very deep because I think there are two regimes that I think people understand quite well now. Well, that's a very good question, and there are two regimes. So to make things simple, let's assume that the amplitude of A are fixed, of X are fixed. So we have Y equals AX plus D. And let's assume that when X is not 0, Xi in absolute value is some value, I'm going to take it to be mu. Okay? And then if mu is large enough, then you can look at the output of L1 regression to unambiguously tell whether X is 0 or not. Right? If your alternative is like this, and mu is large enough, you can look at the output and tell me that x is 0 or not.
So mu has been known to us.
No, I mean, I think theoretically you can calculate the values of mu for which this is true. Okay, so you run the Danzig. If x hat is not 0, then, and you run it with a conservative parameter. If x hat is not 0, you know that x is not 0, right? Because all of a sudden the 0 vector cannot be consistent with 1. That's okay. You violate. Okay, but does it mean that it's good enough? That is, suppose now you take the same signal but you reduce the amplitude. Maybe Danzig would actually output x hat equals 0. But it doesn't mean that the signal is 0. It means that the amplitudes are small enough that you prefer to declare that they're 0. Because if you were not, then there are lots of 0 things that you start estimating, and so the mean squared error will blow up. Does it mean that you're not detectable? No, it does not. And so there is essentially, in this literature, there is 2 thresholds. One is a threshold for estimation, which on our threshold scale is here. And when it says that above this threshold, if the entries are significantly above this threshold, you can reliably detect or tell whether these entries are 0 or not. Below this threshold, you cannot. But you can still detect that x is not 0, but you cannot tell me which coordinates are 0 and which are not 0. But you can feel, but you're not seeing Gaussian white noise. And below, it's the 2 hypotheses are so close that you cannot tell them apart. But there's this whole gap between estimate, reliable telling which coordinates are 0 and which are not, versus this gap where you can feel. It's like when we do ANOVA. Right? When we do ANOVA in statistics, we see that the ANOVA test is significant. But if I say which group is responsible for this departure, you cannot tell sometimes. What you feel is that there is an overall effect that is significant, but you cannot point your finger to it. And that's the same problem here.
And this threshold must depend on sigma squared.
Yeah, of course.
And
Yeah,
so do we have uniformly consistent estimators of sigma squared that work for any range of model dimension?
If I'm, there are some proposals that whether they are provably good, I'm not sure. But yeah, you could try to do by cross validation. There are ways of trying to do these things. It's not solid theory at this moment. I mean, we heard some solid theory yesterday. I don't have such solid theory. Of course, this threshold depends on sigma. What I'm saying is that there's a whole zone where you can actually reject with high confidence that x is not 0, but you're in a zone where you can also not tell which coordinates are not 0. It's because of which component that you're not 0. You cannot tell, but you can tell that you're not seeing z. You're seeing z plus something else.
Was your question to that?
We talked about the oracle estimate. You assume A is identity for the moment and that later on for the general case A. Do we still do that?
No. It's if you suppose you have the restricted isometry property. But the thing is, what if I decide to put a signal on a portion of A? So to get a meaningful oracle, we're going to need that somehow what the problem is identifiable. Okay, so where was this? Yeah. So maybe I should go back here. What I'm assuming about the design is that if I know that the solution has some fair amount of sparsity, that the oracle tells me the support on, and then I need an assumption that even if I knew the support, and if I had no noise, I should be able to recover X. So I better make sure that A has full column rank on that support. And so what I've made my calculation is assuming that we have something like the restricted isometry property, that every small subsets of columns are their eigenvalues around 1, which is the hypothesis you under when you're doing this oracle inequality, since you assume the restricted isometry property. So, but it's any A obeying the restricted isometry property. Does that answer your question?
We have algorithm to work out index set I.
No, but the ideal estimator is not achievable because, you know, you can spend exponential time fitting all least squares model. How do you know which one to pick? You need the oracle to tell you, and the oracle, because to know which one achieves the smallest mean squared error, which is what we have here in the case of the identity, or in the general case, it's a minimum over all possible subsets, but to calculate the minimum mean squared error, I need to know x, and I never know it. That's why it's ideal. It's not something I can use. So maybe it's my mistake. Maybe I did not emphasize enough Oracle that knows so much, has so much side information, needs to know x to be able to tell me which, but in practice I would not know x. That's what I'm trying to estimate after all. So how can I minimize among all possible subsets this mean squared error when I don't know where the argument is? That's what I'm estimating. Right? So this is not achievable. That's why we use it as a benchmark. And we say, given this wonderful information of having exponentially sensible estimators, an oracle who knows the true value of x can give me the best in this family for that x, because now if x changes, the ideal estimate will change too, right? Like on Monday, x is supported on the first few columns, and the oracle say, you know, why don't you just regress the response on the first few columns? The next day it's supported elsewhere, and so on and so forth. Of course, the oracle, the best subset depends on x, so it keeps on changing, and I cannot. What the result says is that, of course, I cannot use this since I don't know what is x, but the theory says that I don't really need to know, have oracle information since I can get close.
Well, maybe we should adjourn for tea. Let me just remind you, though, that there's a talk at 4 o'clock by Carola Schoenlieb. And let's thank Emmanuel again.